Let me show you a picture of softmax function. And they're very similar in that they are used for assigning to every feature distribution a class. In the case of Sigmoid, it will be a binary classification. In the case of softmax, it will be multi-class classification. But we have this S-looking curve. And if a feature is, below the threshold, it will be given 0 if it's binary and 1 otherwise. Let me first begin with a binary example, and then we can generalize it for multi-class classification. So before I talk about softmax, let me talk about sigmoid first, because it's easier to talk about. It's easier to derive the sigmoid function because it's binary. And the prerequisites are this. I'll just take you to this other application I've built. I used to sometimes use this for teaching. It's called BoxMap. Let me bring this over here. Okay. So these are in order for us to understand the sigmoid function, otherwise known as XBit, these are the prerequisites. So I'm going to open each box and quickly take you through the explanation. The sigmoid function is given by this formula. So let's see what this is. Why this? Okay, so let's look at this derivation. First of all, the number of probability is a real number between 0 and 1. So, and it's given by, this number is given by a ratio. It is the total outcomes in the denominator and the chosen outcomes on the numerator. So for example, let's consider flipping a coin. Or flipping 2 coins. And you want to know what is the probability of getting either heads and tails or 2 tails or 2 heads. The total number of outcomes are these 3. You can get 2 heads, 2 tails, or 1 heads and tails. And this is a combination, not a permutation. So we don't care about the order of the coin. So it doesn't matter if you get a tails or heads or tails, it's the same thing. And you want to know what is the probability of getting 2 tails? Well, there's only one such outcome from your total number of outcomes. So that's 1/3 or 33%. If we can round it up to 34% if you want. The chance of getting a tails and a tails when you flip 2 coins is 33%. That's probability. Okay? A similar example is flipping 1 coin. How many outcomes do you have? You only have 2, heads or tails. So what is the probability of getting a heads? 50%. Your total number of outcomes is 2, and then your chosen outcome is 1. So 1/2, that's 50%. Of course, assuming you have a perfectly balanced coin. Then we have odds. Odds is the ratio of 2 probabilities. For example, you want to know what is the probability of getting a let's say you have 2 people who are making a bet. And we want to know who has a higher probability of winning the bet. One person bets on getting a tails and a tails. The other person bets on getting either heads or heads or heads and tails. So they have a higher probability because they have more, their number of chosen outcomes is greater. And you might say this is unfair. Well, so is the real world, right? So for example, in horse betting, people who can buy more bets have more number of outcomes. If they bet on more horses, naturally have a higher probability of winning. Whereas if I put all my money on 1 horse, well, I have a smaller probability. And that's what odds is. The odds of that, let's say you have bet on 3 horses, or in this case, let's say it's 2. Because you have your number of outcomes is close to the total number of outcomes, you'd have a higher probability. So if you compare your probability versus my probability, that's the odds ratio, the odds would be in your favor. You would have twice, the odds of you winning is twice as high. We don't say the probability is twice as high, you say the odds is twice as high. Because if we divide your probability over my probability, we will get 2. Okay? Now, another way to re-express the same ratio is to take my probability and subtract it from 1. Why? Because, well, there are 3 outcomes, three possible outcomes. I have taken one of them. So there are 2 remaining. So out of the 100% of the outcomes, I have taken 33% of it. That's what 1 minus 3 is. Oh, that's why we have 1 minus p tt. So if I had no, if you had taken all 3 outcomes, you would have 100% probability of winning because you have bet on all 3 outcomes. But if I take one of them, you have 1 less than the entirety. That's why you have 1 minus ptt. Either way, you will get the same number. Okay. Now, why do we want to re-express the problem, express the odds ratio in this way? Because this is going to bring us to log odds. The log odds is about taking the, now if you see here, what we have done is we have inverted the ratio. Okay, so this was p of x in the denominator and 1 minus p of x in the numerator. Here we've just flipped it. I just reversed it in the previous example just so you can understand the odds. In the analogy of 2 people betting, and one has they have the luxury of more chosen outcomes than the other person. But if we flip it around, we will get we will still have the ratio, but we have a problem. The reason we use logarithm in any context of probability, so there's something called likelihood and maximum likelihood. You may have heard of this. The reason we use a logarithmic function is to change the scale of the probability. You see, the number can be very small. If I have, for example, 0.05 probability over, let's say, 1 minus p of x, it will be 1 minus 0.5. You see, the probability is very small, 0.5%. And in the case of multi-class classification, you will have all of these very tiny probabilities, 5%, 1%, less than 1%. So for arithmetic purposes, and in particular computation purposes, we want to kind of rescale the probability. So for example, if I take 5% and I put it in the logarithmic function, and the base of the logarithm is not really important, I have changed the scale. So it's now negative 1.3. Okay, so really, what I want to get across is this. The choice of the base is not that important, but we want to apply the logarithmic function just to change the scale. And of course, log base of e is just a natural logarithm. Okay. Then we have the logit function. The logit function is really that. When you apply the logarithmic function to your odds, that's what you call the logit function. So let me zoom out. So the expression we saw previously, that's the logit. And it turns out when you evaluate this expression, it is the same thing as evaluating beta sub 0 and beta sub 1. Now, what is beta sub 0 and beta sub 1? These are the coefficients of the regression model. So did I reference the regression model anywhere else? Not here. Let's move this up here. And for simplicity, let me remove the other variables, and let's just say we have two variables. The epsilon is the residual. That's the error rate. let me not include that in here either. Let's just really keep it simple. And let's just have beta sub 1. So beta sub 0 is what we call the bias term, or the y, it's the number on the y-intercept. So in the ReLU function, the bias was on the x-axis. In the general regression model, the bias is on the y-axis. This is the y-intercept. And this is the x sub 1 is the feature, and this is its weight. Now we'll talk about real estate, size of the property, number of bedrooms, etc., etc. X sub 1 is one feature, and beta sub 1 it's the weight associated with it, the correct weight associated with it. Okay, that's where beta sub 0 and beta sub 1 come from. So if we return to this the logit function, the numerical value that we will get from evaluating this expression is the same as that expression. Now, if we want to get rid of the logarithm, if you want to change the scale again, we will have to take this expression and raise it to the exponential function to eliminate log. And that's what we're doing here. We've taken the expression above and raised it to e, but this is algebra, so we have to do it to the other side as well. Then, of course, e to the power log e will get eliminated. And this expression, this expression comes down here. Now, in order to derive the sigmoid function, we have to do some algebraic manipulation, which is going to be a multiple steps. So what I'm going to do is I'm going to avoid that. Instead, what I've done is I have created, if you can go to symbol lab, which we looked at before, to basically move 1 minus p of x to the other side. And then after a little bit of algebraic manipulation, we get this. This is the formula. Basically, this is odds. This is the odds. In the context of binary classification, we're asking, what is the probability of it being this class versus being in that class? What is the probability of being of this particular feature being fraud versus not fraud? What is the odds of this being well, actually probability. So we have taken the concept of odds and we are now representing as making it a probabilistic number. So what is it now, the probability of being spam versus the probability of not being spam? What is the probability of it being an animal versus the probability of it not being an animal? And that's the idea here. Okay, so this was very sped up explanation of the sigmoid function. So what we will do is then every time we get a feature, it will be its value will be inside the probability of it being in the class versus the probability of it not being in the class. Okay. And so that's what the sigmoid is going to do. If it goes above the threshold, we'll classify it as, let's say, fraud. If it falls below the threshold, we'll classify it as non-fraud, binary classification. So the observations will end up here or down here. Yeah, and apparently sigmoid is a term used in medicine as well.